about to finish up. We're in good shape. And she's here about halfway through with her North American tour. And she's going to tell us about the galaxy.
Thank you all for coming to my talk, and thank you for the kind hospitality here at CITA. It's my second day here now, and my last day here. So if you have any questions, well, if you have any questions during the talk, please interrupt me and I'll be more than happy to explain. If you feel like you shouldn't interrupt me, you can also talk to me afterwards. Let's get started. I am using cosmological simulations for everything I do. So we take a big part of the universe, either a volume that's 25 megaparsec on the side or 100 megaparsec on the side, and we put in fluctuations that are measured from the cosmic microwave background and cosmological parameters. Gravity then causes all this structure to arise automatically. So I'm showing you the gas density, but it would look almost the same if I had shown you dark matter density, because it's only gravity. So to first order, everything's just determined by gravity. So just contracts and everything. If we now, however, zoom in, so I'm showing you density and temperature. This is just a small region of the full volume, a 3 by 3 megaparsec region. And we're zooming into the most massive protocluster. And you can see that. So a very little shock forms, so stuff gets shock heated. And you can also see that there are things being blown apart. That's the feedback that we put in. And that is very important for, so not for the large scale structure, but it's very important for what a galaxy looks like. And that's what I'm investigating here. So I'm looking at how galaxies form and grow throughout the, maybe compared to what other people study, it's a relatively low redshift, but showing you most of the things I'm going to show you is red redshift too. So it's still relatively high redshift.
So this is a cluster?
This is a group. It's a group of galaxies. It's it's 3 megaparsec on the side, so it's pretty large, but it's not one virialized structure yet. It will grow into a cluster. Okay, so the simulations I'm using are called OWLs for overwhelmingly large simulations, and they're mostly overwhelming in how many there are. There are 50 of them or so, which is incredibly many and far too many to tell you about today, but that's fine. I just picked the interesting ones. And because the idea of the OWLs project is that you take one simulation, one just guess at how the universe works, and then you vary every little piece of things that you're not sure about in the simulation. So you can add some feedback or not have feedback, have a different prescription, different parameters, with or without meta-line coding and all that stuff. So I'll be talking about how that changes the growth of galaxies and halos. So I'd like to start with first telling you about the different phases in the universe, I guess. So divided it up. This is just as an illustration. This is not actually my method of identifying these things. But we have the diffuse IGN here, so that's okay. So the average density in the universe is here at 0, because I'm plotting temperature versus overdensity. Log, so it's at 0 is there's the average. So everything that's negative is underdense. But you see that most of the gas is actually in this diffuse IGN phase. It's stuff that's on some sort of temperature density relation because it's being heated by the UV background, and it's cooling because the universe is expanding. So those are the two processes that determine this slope. And when it reaches about 10 times the mean density of the universe, well, most of the gas starts decreasing its temperature, and this is because radiative cooling, the gas becomes dense enough for radiative cooling to become important. So that's what's happening here. Then the gas over here has been somehow shock heated. So there's multiple ways of shock heating, but the UV background cannot make gas be this hot, be above 10 to the 5 Kelvin. So all the stuff that's here is either shocked by a very little shock when it's accreted onto a structure, can be a filament or a halo, or it can have been shocked because of feedback, because outflow was in an outflow and it collided with something. So we call that the warm hot intergalactic medium, and the stuff that's really, really hot can only have shocked on a cluster because those things have high enough virial temperatures to get the gas above 10 to 7 kelvins. And cooling is very inefficient in these regions, so this stuff is expected to stay hot for a long time, especially if it doesn't have a very high density. Then the gas that's in here, in the cold halo gas phase, is gas that is in a halo, but not at a high enough temperature. So this is stuff that's very efficient cooling. It's cooling so it reaches high densities easily. It's cooling onto this star-forming phase. So this is the stuff that we cannot resolve in our simulation because it's the ISM of a galaxy is actually multi-phase, so you have a hot phase and cold phase, and we cannot do this with the current resolution, so we just put it on an equation of states and then it forms stars according to the chemical gradation. So, having defined these phases, I just wanted to show you how the universe evolves. So all the gas at redshift 6 is in the IGM. It's not doing anything. It hasn't been shock heated or anything. Then from this IGM, we start forming a lot of cold halo gas, and from the cold halo gas phase, we form the ISM, and we get more and more stars. Because we have these massive objects, we start shocking a lot of gas to high temperatures, so the warm-hot intergalactic medium starts becoming very important. So by redshift 0, it will be as important as the IGM. So this is mass-weighted, so not volume-weighted. And actually at redshift 0, you can see that the fraction of gas in the ISM is actually decreased with respect to what it was at redshift 2, because there's less star formation at lower redshift. This is just to set the stage. So I'd then like to talk to you about my own research. So I'm showing you one example of a 10 to the 12 solar mass halo at redshift 2. On the top row is the density, bottom row is the temperature. And this is the same halo but in 3 different simulations. So on the left there's a simulation without metal line cooling and without supernova feedback. In the middle there's a simulation with supernova feedback and metal line cooling. And on the right there's a simulation with additionally also AGN feedback. Okay, so I'm now first going to talk about how fast the gas gets from the IGN into the halo, and then after that tell you how it then gets from the halo into a gas. So just to say as well that it's important to add feedback. These are observations of these gray points are observations of the cosmic star formation rate density, and the simulations that do not have any feedback massively overproduce stars at low redshift. So this is the motivation why you would like to put in feedback, because otherwise you just end up with far too many stars at redshift 0. So without any feedback, if you plot a specific accretion rate, which is just the accretion rate divided by the halo mass versus halo mass, you get something that's approximately flat. This is because the accretion rate just scales linearly with halo mass. And this is also true for the dark matter accretion rate. If you plot that, it's also completely flat. Now, this changes when you add feedback, but it doesn't change that much, but it changes by a factor of 2 or 3. If you add supernova feedback, low mass halos accrete slightly less, and the same is true for AGN feedback, which is actually the green one over here. If you add AGN feedback, the halo accretion rates are also a factor of 2 lower. So it's not really impressive, but it is showing that these galaxies in the center of halos are able to produce outflows that also manage to leave the halo, and they start pushing away the gas that would have otherwise accreted. Adding metal line cooling, however, is completely irrelevant, because the blue and the red, the difference is metal line cooling, they're just completely the same. So cooling is not important if you want to get gas into a halo. Feedback is slightly more important. And you can also see that you need AGN feedback to actually reduce accretion rates for high mass halos, because you cannot do it with, you don't do it efficiently with supernova feedback, because there's not enough energy in these outflows. The story is slightly different for galaxies, because the galaxy accretion rate is this dashed curve. So for high mass halos, well, for all halos, the accretion rates for galaxies is lower than the halo accretion rate, but for high mass halos, this is, well, the difference is much larger. And this is because if you get into a halo, a high mass halo, you heat up to a very high temperature, and the cooling rate of the gas is just very, very slow there. So this gas just sits there in the halo and takes a long time before it can reach the galaxy. So this is why with higher halo masses, you get lower galaxy accretion rates. And the peak of the specific galaxy accretion rate is about at 10 to the 10 solar mass halos, and these are then the halos that have the most efficient galaxy growth inside them. This changes, however, if you add supernova feedback, because it reduces low mass, the galaxy accretion rate in low mass halos massively, an order of magnitude, and it makes the most efficient halo growth for galaxies in a halo of 10 to the 12 solar masses, the most efficient. And including the supernova feedback actually increases the galaxy accretion rate for high mass halos, because the gas that would have otherwise been locked up in low mass objects is still left over at a lower redshift too, and still able to accrete onto a high mass galaxy, just because it's not inside a galaxy or in stars yet. In this case, cooling is important, so if we add metal line cooling, it increases the galaxy accretion rate by a factor of 2 for most halo masses, so actually makes the problem that we have that too many stars form, makes it worse, but because we know that there are metals and they will be cooling, we have to add it, so it makes our lives more difficult. But now adding AGN feedback again decreases the galaxy accretion rate also by up to an order of magnitude. There's like a discontinuity here, because I'm stitching together the two simulations that we have, one in a big box, so it's lower resolution, and one in a small box, so it's higher resolution. And they're not completely converged, but still the effect goes the same way. If you add feedback, you have the accretion rates go down. So it's not just ejecting stuff from a galaxy, it's also preventing other stuff for entering a galaxy. So there are two ways of entering a galaxy. There's the hot mode and the cold mode, which is not something that I came up with, but many people, like 8 years ago or something, that started. So if you have a halo that's not spherically symmetric, you can have, well, you will have something that looks like this. It's not spherically symmetric. It has like 3 filaments or so. So the galaxy is here in the center, and the filaments are over here. And you can see that the diffuse gas is actually also hotter, and this is the radial velocity, so it's mostly outflowing. Whereas the denser gas has a lower temperature and is mostly inflowing at high velocity. So these are, if you want to get gas into a halo, you can either go via this, you can shock heat, get a high temperature and slowly cool down, or you go via these filaments and you do not experience a virial shock near the virial radius. At some point you will shock, but this might happen inside the galaxy, and we're not looking at that, we don't even resolve that, but it definitely does not happen at the virial radius. So,
what fraction of the gas in the filaments is down in the halos?
yeah, ask me again.
What fraction of the gas in the filaments that's being larger in this galaxy is itself smaller halo?
So this is not completely clear because you will be limited by your resolution. But if you do like a 10% of the halo mass or so you say everything.
Well, what mass halos can you resolve?
In this simulation, you can do. So this is the high resolution one, so you can do a few times 10 to the 9 solar masses halos. And then it will be like 10%, maybe, it depends on the redshift also, but of the order 10% will be locked up in like in other galaxies, or other halos, other structures. Smaller halos. Or major mergers, that's also possible, but those are rare.
And how is that fraction sensitive to like feedback?
That fraction is, I haven't looked at that, but I imagine that it is, well, I mean, so I have just excluded it because I'm looking at smooth accretion. And I wasn't that interested in it because it was only of the order 10%. So I imagine it's slightly different because you lock up less gas inside the halo, but this will change it by a few percent, so not much. Okay, so if we then check the complete temperature history of all gas. So for all the gas that has recently entered halo, so this is again redshift 2, we check its temperature history for the entire simulation and see what the maximum is. And you kind of get these two populations. So you have one that follows the virial temperature, and another population that's just around 10 to the 5 Kelvin. And you can divide these two however you want, however way you want, but I've chosen to use a fixed maximum pass temperature threshold because everything that's hotter than this is in the phase of very slow cooling, very inefficient cooling, so inefficient accretion, and everything that's colder than that is in principle able to cool down efficiently. But maybe if you're more interested in seeing whether something virial shocked or not, maybe you would like to have a virial temperature criterion that can also work fine. You just, I just want you to keep in mind that at low halo masses, so below 10 to the 10.5, 10 to 11 maybe, there is no bimodality. You have bimodality, clearly you have one for high halo masses, but there's only one kind of gas for low halo masses, just because the virial temperature of these things is so incredibly low that nothing can shock because there's just no hot virialized halo. So looking at the images, what this looks like. So these are 5 halos from high to low mass. And on the top there's the density due to cold mode gas, and on the bottom I've plotted the density due to hot mode gas. So you can see that for a high, so 10 to the 12.5 solar mass halo, there's a big hydrostatic hot halo, and it's being penetrated by these cold filaments. And in a low mass galaxy, this is 10 to the 10.5, there is no hot halo, but there is still, this thing is still forming inside the filaments.
So no viscous forming.
So there is a disk, but this is 4 times the virial radius, the size of the image. So the disk is this thingy in the center. It's only the really high density stuff. So you could zoom in and you would see, in some cases you see very pretty disk, in some cases it's more like a wreck, like because there's also mergers going on inside. So if you then take a central galaxy and you can then check what the properties are of gas at a certain distance away from it. So I've just taken shells around a central galaxy, and then now I'm showing you the fraction of gas that is in the hot mode, and the virial radius is here at here in the middle. So you can see that this is where, again, 4 10 to the 12 solar mass halos, and this is where the hot mode is dominant, whereas close to the galaxy is 10% of the virial radius, well, less than 40% is hot mode, so this is dominated by cold mode gas. This already tells you that of the gas that's sitting at the virial radius, it will be easier for the cold mode gas to get to the center than it is for the hot mode gas to go there. If you look at 10 times the virial radius, you're not actually looking at anything that has it doesn't have much to do with this galaxy that is super far away from this gas. So you're looking at, you're just kind of probing an average IgM warm hot intergalactic medium region. So it's not, I just wanted to say that you don't think that this is also all caused by this central galaxy. It's not just different in temperature, as I already said. It also has sort of cold mode gas. So I'm plotting the median properties. So the cold mode gas, its median is about an order of magnitude, maybe slightly less, higher than the hot mode density, and the spread is much larger. So it is much clumpier. It's a much wider distribution of densities. The metallicity, the median metallicity of cold mode gas is lower than the median metallicity of hot mode gas. This is not converged, so if you go to a higher resolution simulation, the difference will be larger. But again, the spread in the cold mode distribution is much larger. This is because some of it will have been in the vicinity of a recently formed star, and will have enriched it. It could even be like a clump, and inside of it there is a star forming. And some of it has not, well, it's just pristine, it has zero metallicity, which causes the spread to be huge. And quantify the radial velocity, so everything that's negative below zero is actually inflowing. At the virial radius, the hot mode is, well, it's distributed around zero. There's a lot of stuff flowing out, a lot of stuff flowing in. And the median cold mode velocity is actually minus 150 or so. So this is stuff that's going really fast. The fact that this decreases slowly towards the center doesn't mean that these things slow down gradually. It might just be that they still experience shocks and have sudden differences in their velocity, but just because I'm looking at the median, you won't see the individual shocks. I'd also like to point out that if you look at gas that's next to a galaxy, there is no difference in these two modes anymore. Like the gas that makes it there has cooled down, has reached a high density, and is actually all at the same velocity. So the biggest difference, the differences are present at the virial radius. Now, how does this then?
So the cold mode stuff, is it just really this lumps moving along the radius, or is it a really dense one?
It's both.
Okay, but what I would think would be quite lumpy, right?
So
is it more lumpy? Is it more lumps or more sort of dense? Flows along
you mean is more mass? Well, it depends on where how you define clumps. So where you draw this,
so
where
you
you draw
have a
this line.
statistic, I guess. Just measuring density. Like high density could be it's in a lump, or it could be it's smooth screen.
true. Well, these things, I mean, it's hard to identify really small clumps. I mean, you can identify like satellite galaxies that are also present in streams, and you can, well, those are not the main contributors, but like these smaller clumps, I mean, they're not really resolved, so it's hard to say. So everything might be in clumps.
All I'm saying is that this seems to be related to the substructure problem. You see all these subhalos and galaxies, dark matter simulations. So these are like the dark matter or plus gas lumps that are falling in off forms and becoming part of the galaxy. I'm just wondering, or if this is actually just a dense river of gas.
Yeah, so it is mostly a dense river, but I cannot, because I mean I'm limited by resolution, so I cannot exclude it that if you go to higher resolution, you will reach higher density. So I mean, then maybe everything is in super tiny clumps, but they're definitely not in. The majority is not in minor mergers, but it might be in smaller clumps. Maybe not everything though, because there will still be distribution, but they're dominated by the clumps, these high densities. So now, why even people who care about the galaxies themselves, like the star formation rates of galaxies and the global star formation rate of the universe? So how this affects the global star formation rate density is as follows. So I'm showing you a simulation that does contain AGN feedback because it's the only simulation that we have where we get a drop. So between redshift 2 and 0, observations show that the cosmic star formation rate density drops by an order of magnitude. The only simulation that we have that does that is the one that includes both supernova feedback and AGN feedback. So we've used this one because it's the only one who's realistic in this sense. So I'm showing you the star formation rates in the simulation. And this is the halo accretion rate density. So it's much higher. So it says that most of the gas that gets into a halo never manages to form stars. And now if we break that up into hot mode and cold mode, we get the following. So the hot mode accretion rate density keeps increasing towards lower redshift because we form more and more massive objects where hot mode accretion dominates. But the cold mode accretion rate density starts dropping after redshift 3. So there is it peaks around redshift 3, and the cosmic star formation rate density peaks around redshift 2. So there is a delay because it's going to take time for gas when it gets into a halo to reach the galaxy, and then there is a certain star formation time scale. But we can already see that the drop in the cold mode accretion rate density is the only thing that can be causing the drop in the star formation rate density. And we can, so this is for the accretion rate of the halos. I can show you the same thing for the galaxy accretion rate density, which is the black line, and it's completely dominated by the cold accretion rate density, just because there's very little hot mode gas that ever gets into galaxies. This would be, as I said, this is with including AGN. If I had not included AGN, the most massive objects in my simulation would have not had any efficient feedback to prevent star formation, so it would have formed far too many stars, and it forms those stars from hot mode gas. This dashed simulation is the one without AGN feedback, and at redshift 0 you can see that the hot mode accretion rate density starts dominating over the cold mode accretion rate density. So what I just said, that the cold mode is the only important thing, is only true if you have efficient feedback. Otherwise, you'll get too much hot mode accretion and too massive galaxies in high mass halos. But can we, oh, I have some arrows to see the difference. Can we now observe these things, or is this just a fun exercise for a PhD student to do? I think yes, we can, and we have. So I've worked with Gabriel Altai, he's in Durham at the ICC, because he has post-processed our simulations with radiative transfer, because, well, to match the neutron hydrogen column density distribution function. So these are things that so you can observe the line alpha force, the damp line alpha systems, and line limit systems by looking at the quasar and seeing what kind of absorption systems you find in the spectrum. So there's many observations of these systems, so you can compare your simulation to it. But if you just take the one we have, it's completely optically thin, so it's not realistic, because the gas will actually be shielded from the UV background, and well, you have to take the self-shielding into account. So if you then check with radiative transfer what part of the gas is self-shielded, you can correct for this, and you can get a very nice fit to the observations. Observations are in red, and the simulation is in black. It actually goes down, so this is the column density. I've cut it off at 10 to the 16 because this is the part that is shielded, but it's also a good match for the line alpha forest at lower column densities. So this is not something that I have done, but I have used his data, so the stuff that he calculated, to see what's doing the absorption here. What are these systems? So I can take my simulation and only select a fraction of the gas with whatever selection that I want. So I get, so here I have chosen to only include gas with a maximum temperature below 10 to the 5.5 Kelvin. So I'm calling that the cold mode gas. And seeing, just adding up all the neutral hydrogen in a specific sideline in my simulation, and seeing what fraction I recover. So for the same pixel, I do it for the full distribution and for the my selection only, and see what fractions recover. So you can see that if you do this with this maximum past temperature criterion, you actually recover most of the absorption in the universe. Only for the very highest column density it goes down to 70%, but for everything else it's above 95% of stuff. This is maybe not so super impressive because most of the gas in the universe will be in the IGM, so you don't expect it to have a temperature higher than 5.5 Kelvin. So I'm showing this at register 3, by the way. I haven't mentioned it. So you think maybe it would be more impressive if we knew where this gas was. So the black line shows you the fraction of the gas, the fraction of the H1 absorbing gas that is inside halos against column density again. So you can see that for, well, above 10 to the 18 per square centimeter, 80% of the absorption, more even, is by gas that is inside a halo. So it's both inside a halo and it is cold mode. Most of this is in the main structure, and 20% is in resolved substructure for the people who wants to know about clumps. But this is only, I can only resolve structure down to 10 to the 9-ish solar masses. Oh yeah, so the stuff that's not inside halos actually line alpha forest and line limit systems, and then line alpha systems are all located inside halos. So it may not be called accretion if it's not actually accreting. So we care also about whether this stuff is inflowing or outflowing, or just kind of statically rotating. So I use a quarter of the circular velocity as so if it flows in faster than that, I call it inflowing. If it flows out faster than a quarter of the circular velocity, it's outflowing. And if it's moving more slowly, it's static. So there's quite a large fraction that's just static, it's just sitting in a halo, but the biggest contribution is the gas that's flowing in, and the outflowing gas is actually relatively unimportant. So it is not only cold and inside halos, but it's also inflowing. So this makes me conclude that the systems that we observe, line limit systems and line alpha systems, are proof of cold mode accretion. Because in a simulation without cold mode accretion, we wouldn't see these things because they're all cold mode accretion. They are also important for star formation, as I've already said. So the black line is the stuff that is inside the galaxy. That's the star-forming gas. So this dominates at the highest column densities because it's just the densest region of the gas in the universe. And the red line shows you the fraction of the gas that will be star-forming within the next 1.2 gigayears. So it's not star-forming now, but it will, so not star-forming at redshift 3, but it will be star-forming before redshift 2. So you can see that most of the line systems and the lowest column density line and alpha systems, 70% of those will be star-forming in the very near future. So these things are very important for the star formation history of the universe. Look at the green line. I'm showing you what fraction is doing this for the first time. It's accreting onto the galaxy for the first time. So it was never in a galaxy before. So it's not some sort of recycling something, but it is, it's coming in, it's accreting for the first time onto the galaxy. That's 40%. And another 40% or so was in a galaxy before redshift 3 and is not at redshift 3. So that is all I want to say now about what makes up the this H1 column density distribution function.
So exactly how are these distributed with respect to the zero radius?
So so part of it, okay, so it's dominated by low mass halos. So it's
so we should think of it deep dumped down by analysis with low mass halos.
No, okay, so let me show this. So the highest column density absorbers are in halos that are 10 to 11 to 10 to the 12 solar masses. But everything below 10 to the 21 per square centimeter is dominated by the lowest mass halos that I can resolve, so 10 to the 9 to 10 to the 10 solar masses.
So the highest column absorbers are they basically tech disks?
Yes. So this is all stuff that's inside a galaxy. So it's all stuff that has a proper density above 0.1 particles per cubic centimeter. And so it's dominated by low mass halos, and if you get to higher densities, you will get further inside the halo. That was your question, I think, really. So the stuff that's a lower column density line and limit system will be on the outskirts, and the stuff that's the higher column density will be close to the central galaxies. Might even be already in a disk, but just not yet dense enough to start forming.
I had a question about the past ISM. One of them is stuff getting blown out.
Yes.
So that it's still dense enough to be part of the environment.
Well, yeah, but it can. Well, it can also have been blown out, not have reached the outer halo, and then come back. So it could have gone through a phase of not being a line limit system, or it can have been recently expelled. But as I already said, that most of this gas is actually inflowing, so it's probably already on its way to back to the center. So let me just end with my conclusions. So I've told you that efficient feedback reduces halo accretion rates slightly, but it has a huge effect on galaxy accretion rates. They can increase them by an order of magnitude. Cooling is not important for the fueling of halos, but it is very important for getting gas into galaxies. And these galaxies are fed mostly by cold mode gas that's on average denser, more metal poor, and flowing in at higher velocities. And its combined effect is shaping the cosmic star formation rate density in the universe. And this cold mode gas has already been detected because it's essential for reproducing the H1 column density distribution function. Thank you.
What extent are you able to change your feedback restrictions and see how those changes affect results?
Yes, this is, I have done this. You mean for the absorption system, right? Or, well, I mean, for the galaxy accretion rates, I've shown how this affects the results. Well, I mean, my results in any case.
Well, but I mean, you have a few, well, I'm afraid I missed the first couple minutes of the talk, but you have a few basic methods of feedback, but you know, there's still some arbitrariness in how one defines AGN feedback or
sure, that's true. I have used more simulations than the one I've shown, just because I didn't want to go for 3 days instead of now. So you can make, for example, supernova feedback. You can make it more efficient. So if you're a bit smarter about choosing the velocity of the outflows, you can make it more efficient at higher halo masses, and it changes your results. It changes your.
So on what scale is are you sort of placing significant feedback in the sense that stars are clustered and so on? Are you doing it in a broad brush sense where there's you're doing it on tentative, you're measuring star formation rate and some mass up to a certain size and then positing
so only gas that is high density can form stars, and when it does, it depends a bit on what you want to do, but in the case that I've shown, our reference case, you have when a star particle forms, it kicks 2 of its neighbors with a fixed velocity of 600 kilometers per second. That's the reference model.
And what's the mass of the star particle?
That would depend on resolution. For the high resolution, it's 10 to the 6 solar masses. You can also tune this velocity to be to scale with the halo mass, for example. The AGN feedback heats one of its. So if you have enough energy stored, you calculate the Bondi-Hoyle accretion rate. If you have enough energy stored, it heats one of its neighbors to a high temperature, to 10 to the 8 Kelvin. And this, because it's hotter, it starts expanding and it drives outflows as well. So,
well, in the first case, for example, if I add velocities that are directly away from the particle, and then I do that for a large number of particles, I would think that the resultant energy momentum positive would depend on the draw.
Because it's always if you have you mean with higher resolution, right?
Well, you just imagine this process takes a uniform positive little packets of energy.
So you're saying to keep the amount of energy you're putting in the same to change the number of particles?
Well, if the cooling, then maybe it doesn't matter to use a positive energy. It has to reflect into a larger structure. But if it cools, then and you're more of a, let's say, snow cloud, you use supernova in this. And it doesn't. I think it does matter because the chemical momentum can cancel each other.
Oh, okay, yeah. So this is something that we definitely do not resolve at these scales. So we kind of skip the whole ISM phase because we cannot resolve it. So, and we just say, okay, we know that there is a certain amount of energy. What if? So you can choose some efficiency. So we've dumped in 40% of the energy that's available. We put in this outflow, and we see what the effect is.
But okay, but as you described it, you put in energy into the neighboring particle.
Yes.
Which is still a pretty small scale.
Yes, so then when this outflow is generated,
but then what happens if the gas is rapidly cooling? Does it, I mean,
well, that's why you either put it in with a fixed velocity, so, I mean, it just goes really fast and it drags along its neighbors and it, reaches quite a distance before it's eventually slowed down enough, we've dragged enough of the other gas away with it, or you need it to a very high temperature, like 98 Kelvin, so cooling is very inefficient. There's these two methods that are both work.
And the second one is basically reagent.
Yes, we have a simulation that does supernova feedback thermally too. You just cannot heat the gas around you a little bit because then you will have efficient cooling. So you just have to heat them to a very high temperature.
Well, I guess another way of asking is in the case of supernova feedback, to what extent are the results resolution? You have that fixed velocity, you change your resolution, you get the results.
So actually the supernova feedback is relatively well converged because we skip the whole I guess thermal phase, and we already say we put in a fixed velocity, so it's already going. So this is relatively well, it's not completely converged. If you want to have it completely converged, you can do what other people do is you switch off cooling and make sure that your gas escapes from the galaxy. Then you're converging, but you're converging to the wrong results. And that would also not be a very good idea. So you're right, but convergence is pretty good for the feedback that we've chosen.
All right.
So you like 50 simulations, and the one that you were talking about, you had the using, sort of bumpy, but not too bumpy, dense absorption. Of all of the numbers of simulations you did, how many of them reproduce that curve also?
All of them do.
So then that means that it's easy to get.
Yes, well, easy to get if you're smart enough about your radiator transfer. Then it's easy to get. The only thing that matters, like the only thing that in our suite simulation that changed anything was when we include different osmotical parameters. Sigma 8, if you increase that, you get more H1 absorption per condensed. But for the rest, so it doesn't discriminate between models, which is maybe sad, but at least it's something that is robust to variations in our in the physics that we do not understand.
So I had a really interesting actually. So you mentioned that for the post-processing, we did the self-shielding to get the column density distribution.
Yeah.
Are you worried that not including the self-shielding in the hydro simulations that you're missing something?
Well, yeah. You are missing something for sure, but this only kicks in at very high densities, and I mean it will change your temperature, but these particles are already cold, and they will be colder and denser, but I don't think that they don't just enter a completely different medium. But I think it's always better to add things that you're sure are more visible.